normals. We can calculate a vertex normal for every facet, but we can also calculate where the two facets blend together right here. Right at that point, what is the normal at the vertex? Does it belong with facet A, with facet B, or with facet C? And the answer is, well, kind of all of them, right? So what do you do with the vertices on the vertexes? So one answer is you do the average. Those are vectors, so you do a vector average. Just take the average surface normal of the facets and pretend that that's the appropriate surface normal. All right? So what do you do in between the vertex normals? All right? Suppose we're along this line. All right. Well, we have a vertex normal over here. We have a vertex normal over there. So maybe what you do is do a linear interpolation from this vertex normal to that vertex normal. Okay. So what do you do if you are in between, in the middle? Well, keep on interpolating, right? So if you're in here, you can calculate the relative distance to this vertex, that vertex, and that vertex, and take a weighted average. The further you are from the vertex, the less the weight's going to be. The closer you are to the vertex, the greater the weight's going to be. Same philosophy as going over the edge, except that in this case we're doing 3 vertices. All right, so we can average the normals that are associated with the facets. Okay, that leads to the second of the 3 shading models. The first one is the flat model. The second one is the Garreau model. Garreau's, O-A-U-D. Okay, Garreau model. What the Garreau model says is that we're going to calculate at each vertex, we're going to calculate, do the average of all the surfaces that are touching that vertex, calculate the average normal, and then calculate the appropriate shading at that normal. Okay? Now what are we going to do? Now to get the shading in between, we are going to average the color, or average the reflectance for the 3 vertices. So if we're along here, it's going to be, the average of the color here, the average of the color there. If we're in the middle, it's going to be a weighted average of all 3. So we apply our shading calculation once per vertex, and then we do a trilinear interpolation in between. So that's a little bit more complicated than calculating it once per the entire facet. That's a lot easier. You just do the calculation once and it applies everywhere in that facet. Okay. And they're asking the question, does that eliminate the facet? And the answer is no, not entirely. You can still see the facets, particularly in the area of specular reflection. All right? I can see the facets pretty clearly there. If I look up here, it looks pretty smooth, right? If we look at flat shading, all right, the facets jump out pretty strongly because there's a big change in color from one facet to the next. With Garot shading, that kind of blends together a little bit more, but it doesn't work so well at the, for the specular reflections. Which leads us to the third shading model. And remember I told you that guy Fong pops up all over the place with things named after him? Well, there was the Fong lighting model. That's with the power of the cosine of phi on specular reflections. And here he is again, but this is in the shading model. So this is called Fong shading model as opposed to Fong reflection formula model. All right? So the idea here, and how does it look, by the way? How does that teapot compare? Pretty decent, right? Okay. So the model here is, again, you calculate the surface normal at every vertex. But now, instead of calculating the color at every vertex, you calculate the surface normal by linear interpolation everywhere in between, and then calculate the color based on that surface normal. So in Garot shading, you do the shading model calculation, summing over the light sources, everything else, you do it once per vertex. Here you do it once for every spot on the surface. So there's an enormous difference in calculation between Garot shading and Fong shading. There's a big but not enormous difference between Garot shading and flat shading. So Fong shading gives you the best result at the most computational. All right, linearly interpolate vertex normals, equation at every pixel, blah, blah, blah. Okay. What are they saying? Yeah, if you don't have the facets small enough, you're still going to see it, the individual facets. You'll notice them particularly along the silhouette, along the contour. Right? Interpolation depends on polygon orientation. Yeah, I'm not convinced of the other points as much. Okay, so that's the end of that series of slides. So we are going to turn our attention. What we had first was kind of a general overview of lighting and shading, and now we're going to be talking how does MATLAB do it. All right? MATLAB, of course, uses these models. Right? So basically, we can select face lighting and edge lighting properties of patches, and our choices are flat, Garot, and Fong lighting. And I like this example because it shows kind of all three of them, all four of them simultaneously, whereby all four, if you just use ambient light and ambient reflection, you don't worry about directions or geometry or anything. It just comes out a single shade. So that's the none there, means we're not going to do any shading. We're just going to assume ambient effects. So this is flat shading. Everywhere on the facet is constant. Here's Garot shading. which does a pretty good job in here. Not so good where the specular component is, because there's a much stronger geometry effect near the specular highlight. And then the thong shading doesn't do a perfect job in here, but it's much improved compared to the Garot shading model. So MATLAB has a function or a specification that allows you to choose from one of those 4 different choices. Okay, then MATLAB allows you to define lights for the scene. Okay, and in the lights, it's either going to be, well, the color of the light. By color, they also mean intensity, okay? Because they will, if you have a red light, they'll adjust the value of redness according to the intensity. So it's the product of the color times the intensity that gets used in there. Okay, they're saying, well, style is either infinitely far away, the default or local. I would prefer to think of that as point source or directional source. Okay? So, for directional sources, it's the angle that's important. For point sources, what they're calling local sources, it's the location that's important. All right. There is a light function, and a light source you can define the strength of the ambient term, the diffuse term, and the specular term. Actually, this is, yeah, there's the light objects. On the patch, when they talk about ambient strength, diffuse restraint, specular restraint, they're talking about the reflectance of those 3 terms. Then the specular exponent, that's the n value. And I'm not sure what specular color reflectance means in this case. So when you talk about the light style, it can either be infinite, meaning directional light, or it can be local, meaning a point light. Then there is a position. So in the case of local, position specifies a point source location. If it's infinite, the position 3 vector defines the direction of light coming in. So here is an example. We're defining a surface. This is the standard MATLAB surface. We've done that before. And here's how we apply the lighting. We're going to set the face lighting to Phong, so it's using the Phong model. The face color, we're going to do interpolation. Okay, the ambient strength is 0.5. And this model, I can see the other terms, the ... This doesn't quite look like an ambient model to me, but go figure. We'll look at the MATLAB. And here the light has a style is infinite, so the position is a vector. So the light is coming in direction of 1, 0, 0. I'm guessing they're trying to say it's coming in from that direction. switch to MATLAB. Now that produces try example 2. Okay, so when we say 1, 0, 0 for the direction, I think we mean the light is coming from that direction, because obviously the light's coming from right to left, right? We can test that. Put a negative sign in there. Now the light's coming from the left, from the negative direction, and going along the positive direction. There's a function called material. Okay. Wow. Okay. We'll do what they suggest here. Oh, how about this? We'll do get material values, material default. it should be an argument. No, it doesn't. Well, sure, that's what I mean. Then why doesn't you work? All right, so unless someone figures it out before me, I suspect that there are values already defined for the specular and the diffuse, and all they're doing is overriding the ambient. One way of testing that is to make no ambient. Okay, but we're still looking, you can still see where you're close to the light. You can see that there is a diffuse and a specular term in there. All right, back to this. So even though they haven't set the values explicitly here, they're still hiding there. Okay, if in the previous example we defined a direction according to the coordinate axes, the direction x, y, and z. We can also define it according to the local azimuth elevation of the view. So that means we can call the light angle, we can give it an azimuth elevation, and that will create a light with a style of infinite coming from that angle. And here we're going to do a movie, except I would need to upgrade the MATLAB to do the movie. No, it doesn't like that. Okay, so what that is doing is, at least it's not doing it because I've still got the PowerPoint up there.